Hello everyone. Welcome to part 6 in our series on using Laplace transforms to solve differential equations. Today we're going to be talking about inverting transforms. Okay, let's quickly review the process by which we use Laplace transforms to solve these differential equations. Okay, as we've seen in previous videos, step 1 is to take the Laplace transform of both sides of the differential equation. So for example, if my differential equation were f double prime minus f equals 12, I would take the Laplace transform of this side and take the Laplace transform of that side and set them equal to each other. That's going to give us an expression involving the Laplace transform of little f, which we usually denote with big F. Step number 2 is to solve that expression for big F, usually a little bit of algebra. Finally, step 3, and often this is the most complicated portion of these steps, we have to invert this transform to get back to our original function little f. That is the solution of the differential equation. That's what we want. What we have is big F. So it's kind of like going backwards. I have to figure out what little f produced the big F. Okay, and in this video we're going to do a bunch of examples that show the common techniques you're going to need to know in order to do this last step, which is usually the trickiest part. Okay, let's get right to it. Okay, here's our first example. So we've done steps 1 and 2, and this is our transform function. We have to convert this back, we have to invert this transform to get little f of t. Okay, first thing I notice, I have a number on the top, and I've got a trinomial on the bottom. It doesn't really look like a transform of any function we know. But you should be thinking, wait, okay, just a second here. If I look at the transform of sine of t, transform of sine of t is 1 over s squared plus 1. You know, this looks something like that. I've got a 1 on the top, and I've got an s squared. I mean, there is other stuff. There's this unfortunate thing here, 2s. And then I don't have plus 1, I have plus 10. What we typically do to make this look more like this is we complete the square. So let's go ahead and do that. Okay, complete the square. I'm going to divide this coefficient by 2 to get 1, and then I square that. So I'm going to add 1, and then I have to subtract 1 in order to offset that. So this 10 is going to become a 9 when I subtract 1. And this part is going to give me s squared plus 2s plus 1. Well, that's just quantity, s plus 1 squared. And then I have plus 10 minus 1, which is 9. Okay, instead of 9, maybe I'm going to write that as 3 squared instead. I still have 1 on top. Okay, that's why we completed the square, was to get a binomial squared plus a number. And of course, in this case, it works out nicely. 9, when I subtracted 1 from 10, I got 9, which happens to be 3 squared. Okay, great. But now compare again with this. You know, we're getting close. Let me write another one down, and this is helpful when you're just learning how to do these inverse transforms. The transform of sine of 3t is 3 over s squared plus 9. That actually is pretty close. Okay, I don't have s squared. I have s plus 1 quantity squared. I don't have a 3 on top, but these are things we know how to deal with. Okay, let's first take care of the s plus 1. Remember that if I multiply a function by an exponential, it has the effect of changing the s, in this case, into s plus 1. Look at that. I've actually matched the denominator at this point. The only thing I'm missing is the numerator. But actually, that's an easy fix. If I want a 3 on top of my fraction, I'm just going to put it up there. The number I want, I just put up there, as long as I remember, okay, I've got to divide by 3. That way, 3 over 3 still gives me 1. I haven't actually changed anything. These are the same fractions. But now I'm totally ready to go. This part is exactly what I have over here. So we're ready to write down the answer. The original function, little f of t, must be 1/3 e to the minus t sine of 3t. That's it. Okay, let's do another example, a little bit harder than this one, but not by much. Okay, similar scenario here. I've got a trinomial that I can't factor in the denominator. Now I have an s in the numerator, so that's going to complicate things a little bit, but the process is going to be similar. First thing we do is complete the square. In this case, I'm going to, let's see, 6 divided by 2 is 3. I square that to get 9. Then I subtract 9, so 25 is going to become 16. Okay, so what do I get? S is still on the top. I'm going to get s plus 3 quantity squared. 25 minus 9 is 16. Well, that's equal to 4 squared. Okay, so once again, we're going after transforms that look like things we know. In this case, I have an s on top. I have some kind of s thing squared plus a number squared. Okay, that should remind you of something. When I take the transform of cosine, let's write it down. Cosine of 4t. What is the transform of cosine of 4t? It's s over s squared plus 4 squared. This is actually pretty close, isn't it? Okay, this is a kind of a big problem right here. We've got s plus 3. We don't have s. But remember that means we're just going to be multiplying by an exponential, in this case, e to the minus 3t cosine 4t. What's the transform of that? I replace every s with s plus 3, including the one on top. Don't forget that. That's a common mistake to make. Okay, the transform of this function is this function. I've matched the denominator. I don't have the numerator. Okay, that's a problem. But we can match the numerator as well. How do I do that? I'm not going to multiply and divide in this case, but I can add 3. Look at that, I just added 3. Now, of course, I can't just add the 3 and then leave it like that because I've changed things. But if I subtract 3 now, I'm going to put that as a separate fraction. So I've actually kind of broken this fraction up a little bit. But hopefully you'll see that this is exactly the same as this because these have the same denominator. So the numerator is s plus 3 minus 3. That's the same thing as s. Why did I do that? Well, of course, I did it here so that I could immediately match this guy right over here. Okay, is this trouble? Not really, because I'm thinking, hey, this looks a lot like sine of 4t multiplied by e to the minus 3t. Okay, I'm just missing something that I've got to add there. So let's just move this here. Okay. Sine of 4t would normally have a 4 on top. Okay, how do I get a 4? I have a 3 instead, which I'm going to move here. If I want a 4, I just have to remember to divide by 4. So 3/4 times 4, that's 3. That's what I had originally. But now this part is exactly what I wanted. That is the transform of sine of 4t multiplied by e to the minus 3t. Okay, I'm ready to write down my function. F of t equals, this first term here, well, that's exactly e to the minus 3t cosine of 4t. This term is e to the minus 3t sine of 4t with a minus 3/4 in front. So they both have e to the minus 3t. One is cosine of 4t, the other one is sine of 4t. Okay, great. Let's do another example, kind of different, but it's something that you're going to see a lot when you're inverting transforms. Okay, it looks similar to what we've been doing before. However, you notice that in this case, we can actually factor the denominator, and that's what you're going to want to do. If you can factor, go right ahead and factor. Okay, so let's see what we get with that. So s minus 5 And I'm working hard to make my 5s look different. I know s is probably not the best choice of variable, but that's traditional. Okay, how does this factor? Let's see, s plus 1, s minus 2. I think I got that right because minus 2s plus s is minus s, and 1 and minus 2 multiply to give you minus 2. Okay, how do we deal with this? If you can factor the denominator, we actually want to break these up because we don't know any function that transforms directly to something like this. But if we can break up these fractions, then we might have a chance. Okay, breaking up fractions is the process of partial fraction decomposition. Okay, and I'm going to assume that you've seen that kind of thing already. I will go through it, but I'm going to go through it fairly quickly here. Okay, so you remember how we do that. We take our original fraction, and we're going to set this equal to a over s plus 1 plus b over s minus 2. And the goal is to figure out what the numbers a and b are, which make these fractions add to our original fraction. Okay, I multiply both sides by the common denominator, which is this guy. So I get s minus 5 equals, make that 5 a little bit better, equals a times s minus 2. I'm multiplying both sides of this equation by this denominator, plus b times s minus 1. Okay, how do we do this? I'm going to use a process which I guess formally might be called the Heaviside cover-up method. It basically just means plugging in numbers such that terms like this disappear or a term like this disappears. Also, you notice I kind of messed up here. This should be s plus 1. Sorry about that. Okay, for example, if I plug in to this equation right here, if I plug in s equals 2, okay, on the left-hand side, I get minus 3. On the right-hand side, this term disappears. This term, remember I'm plugging in 2, gives me 3b. Therefore, b is equal to minus 1. Okay, what do you think I'm going to plug in next? Well, I think the obvious choice is let's plug in s equals minus 1. That's going to get rid of this term. Okay, the left-hand side gives me minus 6. Let's see, this side is going to be minus 3a, I think. So a is going to be 2. Okay, what does that mean? That means that this fraction that we started with here equals 2 over s plus 1 minus 1 over s minus 2. Wow, look how nice and simple that turned out. It's funny, when you add simple fractions, you can get something a lot more complicated. But why did we do all of that? Well, I'm hoping that you recognize these as transforms of exponentials. 1 over s plus 1 is the transform of e to the minus t. 1 over s minus 2 is the transform of e to the 2t. So I can write down my original function right away. Little f of t equals 2 e to the minus t minus e to the 2t. That's my answer. This function, when transformed, gives me this, and then that actually is equal to this. That's the puzzle that we just solved. Okay, that's it for this video. I hope you enjoyed it, and I'll see you next time.